Yes, good afternoon, everyone. So I wish to present this work on poro-elastic modeling and acoustic response of corroded rebars in reinforced concrete with high-frequency acoustics. I would like to recognize the work of my colleague, Dr. Criswell Moreno, who has actually provided a lot of background information, concrete samples, and is actually performing some additional tests on the samples I will present. And my master student, Matthew Brogdon, who actually presented in a poster session yesterday. So very quickly, for the sake of saving time, here we go. Dr. Criswell, in a previous presentation, just spoke about the importance of tracking corrosion and damage in concrete in the marine environment, which can result in major costs associated with repair and maintenance. As the concrete, pretty much what happens is that as, for the most part, chlorides reaches the rebar in the reinforced concrete, after a certain point, corrosion starts, and that causes the concrete to crack. And I'm going to keep it to this simple explanation, as my background is that of acoustics, and I'm going to focus on how we can use a specific type of model to try to predict how and measure the degree of corrosion that is taking place in the rebar. So right away, I'd like to provide a fairly extensive problem statement, and that is important because there are methods nowadays that exist, and there are problems associated with that. So I'd like to talk about this a bit. So first of all, the detection and measurement of rebar corrosion in reinforced concrete using ultrasonic non-destructive testing, or NDT, has been of great interest for decades, and for obvious reasons. When you use ultrasonic NDT, the operators can monitor corrosion in the reinforced concrete without having to drill through the concrete or cut the concrete. And ideally, we would hope that one can detect early signs of corrosion this way. But the limitation to this approach resides in the ability to successfully detect early forms of corrosion before cracks reach the surface of the reinforced concrete. And again, Dr. Criswell has given me samples where literally the concrete is completely split apart. The idea would be to be able to detect these cracks before they reach the surface. So now recent publications indicate that the scientific community is testing a variety of signal processing approaches to accurately estimate the propagation of crack and changes in the rebar. And that's usually using narrow beam broadband acoustic transducers, which usually operate at hundreds of kilohertz with a spatial resolution of the order of millimeters. Now, these approaches include high order statistics, short time Fourier transform, artificial and convolutional neural network, wavelet decomposition, EMD, Laplace transforms, and these are very well established techniques, and I use them extensively for other applications in my field of underwater acoustics, but they have limits when it comes to the specific problem of monitoring reinforced concrete and corrosion of the rebar. Now, the first limitation is that early crack detection capability depends on spatial resolution, how crisp an image we can create. Now, the techniques presented usually rely one way or another on distance measurement obtained from the time of travel of sound and an estimate of the sound speed in the concrete and the rebar. You try to create one way or another some sort of an image of where the rebar is relative to the surface of the concrete block. That propagation of ultrasound through concrete is subject to great attenuation, mostly due to friction and scattering. And this attenuation increases significantly with frequency, while on the other hand, spatial resolution improves as frequency of operation increases because the effective bandwidth of the transducer increases with frequency. So there is a sweet spot when we use ultrasonic transducer in monitoring reinforced concrete, and it's usually located around 500 kilohertz, so that sound can travel through several centimeters of concrete, reach the rebar, and produce a sufficiently strong echo. All of this with a resolution of the order of 5 to 15 millimeters. Now, I have tested transducers at much higher frequency, but the problem is that quite often the sound does not penetrate in the concrete very, very deep, like sometimes a few millimeters. So you really need to operate around 500 kilohertz to get the best, probably the best trade-off in terms of penetration versus resolution. Now, 5 to 15 millimeters, even let's say we have a really high quality transducer and we have 4 to 5 millimeter spatial resolution, it's not often sufficient to actually do early crack detection. So another thing is one should note that many techniques exist, such as shear probe, contact transducer, focused and unfocused immersion transducers, and that the angle of observation can be adjusted to obtain better results. But it remains that the resolution, no matter what, is really not sufficient to observe cracks a few millimeters long or less, which in turn limits the ability for an early detection. Now, sample observation clearly indicates that in the vicinity of corrosion and cracks, there is a complex structure combining fluid cavities and loose concrete materials surrounding the corroded rebar. And that clearly appears if you look at many of these images you see of corroded concrete. Now, this means that a more appropriate acoustic propagation model could be a poro-elastic model, such as the well-established BO and BO stall models developed for the propagation of sound in the seafloor. Now, this is the model I'm talking about, and that model has been tried for reinforced concrete, but it is a fairly complex problem. The bulk of the effort associated with the BO model is for foundation in the seafloor, study of sound propagation in sediments. It's usually used in both field of civil engineering, for Navy purposes, and not as often for reinforced concrete problems. So in both cases, fluid-filled cavities and the skeletal frame produce coupled vibration induced by the incoming sound, resulting in a dispersive medium, which means that the response of the medium depends on frequency, with two types of compressional wave, the fast and the slow wave, and shear wave. Now, the frequency response of a poro-elastic medium is different in that it is much more accurate than that would be obtained using an elastic or a viscoelastic medium, which are usually the models that are used for with techniques such as finite element modeling and other technique, ANN, CNN, and so on. Now, and I am almost done with the background here. The BO stall model, although complex, has one great benefit, is that it ties the physical property of the porous medium, such as porosity, mean grain diameter, mass density, bulk modulus, shear modulus, and so on. I saw a presentation earlier. It accounts for the tortuosity, for example, in the skeletal structure of the frame. And it ties that to the sound propagation through the porous medium. So the idea is that it is possible to fit a set of physical characteristics of the medium to a specific acoustic signature measured of the transducer. It is a complex problem, but it is feasible. So while the BO model has been extensively used for foundation engineering, again, it remains in many ways a lot of work to be done with reinforced concrete. So what I propose is to use some of the specific techniques that I actually derived, initially inspired from the work of Stern, that actually include and account for depth-dependent property of within the medium, for example, increase in porosity or tortuosity with depth in the concrete up to the rebar, and see how we can actually, from there, infer a possible presence of early cracks. Now, the goal is going to be, again, to detect and demonstrate we can find early appearance of cracks and track it over time. And the objectives are really threefold: to identify the proper measurement configuration and predict the performance, to perform a series of targeted measurements using the proper ultrasonic transducers, and to evaluate the degree of corrosion within the reinforced concrete. Now you can get the detail of this document over here. Now this research would be the foundation for a more detailed acoustic analysis of rebar corrosion detection in reinforced concrete, where we would be able to, with some level of accuracy, detect post-cracking corrosion and possibly detect pre-cracking corrosion. Now, the approach is shown in this diagram. And again, there is a description in text over here of the approach as well. We have a signal generator which produces in our approach a 7 microsecond pulse centered at 500 kilohertz every 100 milliseconds. This is in turn transmitted to an acoustic transducer, which is an Olympus V389. It transmits sound in a cone of emission, which is fairly narrow, and you have the specification in the presentation over here. The sound actually goes from the transducer to the reinforced concrete surface over here, and then travels through the concrete to the carbon steel rebar, and then bounces back. Now, the concrete, the rebar is at a depth H below the surface of the concrete itself, at a depth D below the surface, the face of the transducer. Now, sound as it travels from the transducer to the rebar bounces multiple times, and we use time gating to isolate the echoes that we are interested in. So this is a side view. The x-axis is that of the travel of the transducer. We move the transducer from left to right as we run measurements. And the front view over here shows the alignment of the transducer with the rebar. So we make sure that the transducer is carefully aligned with the rebar at all times. Then after that, when the echoes are received, they are acquired using a digital oscilloscope with an acquisition system sampled at 1.25 gigahertz, stored on the laptop and post-processed. Now, the approach consists of individual steps. We have a data acquisition where I explain we place the transducer at various locations along the x-axis, typically every 5 millimeters or 1 centimeter. And every time we acquire at least 10 records to perform time averaging. Then we identify the first concrete echo and rebar echo using time gating. And then at the same time, using a set of default parameters, we run our BO model to create artificial signals. And we are going to isolate again the first concrete echo and the first rebar echo and verify that measurement and simulation produce reasonably similar results. Then the second step, which is actually work that was presented by my master student yesterday, consists in actually performing a non-linear least square minimization of error, so that in a way, what we do is that we take a certain number of parameters for the concrete: porosity, mass density, bulk modulus, shear modulus, and for the rebar, the mass density, the modulus of elasticity, the distance within the rebar. And we actually allow this parameter to vary within a certain range of value, certain intervals. And we use what we call the trace region reflective algorithm and the Levenberg Marquardt algorithm. We comparatively test them to adjust the physical parameter so that we actually get a better match. In the end, the idea is to record and analyze the change in physical property from the BO model and to establish trends. And we compare these trends against techniques such as corrosion potential measurements, which were presented by Dr. Creswell about 30 minutes ago. And then what we're going to do is repeat the process every month or so. And the idea is that we provide results and discuss with specialists of corrosion problem like Dr. Creswell to see if there is clearly an early sign of corrosion taking place. Now, the approach itself, using this transducer, can help us predict pre-cracking corrosion and post-cracking corrosion. And I realize I have to keep track of time here, so I'm going to go very quickly. But in the case of pre-cracking corrosion, a change in the characteristic impedance of the rebar in contact with the concrete would cause predominantly a change in amplitude of the rebar echo, and also a change in time of arrival due to a change in the diameter of the rebar. Now, the post-cracking corrosion would translate into two phenomena: an accentuated change in the characteristic impedance of the rebar in contact with the concrete, and the appearance of an additional echo due to the presence of forming cracks. Now, it is understood that detection and identification of pre-cracking corrosion is going to be much more challenging than post-cracking corrosion. The technique would be better capable of identifying early signs of post-cracking than pre-cracking situation. Now, here's the progress to date. So I'm going to show a diagram here. We have this Olympus Parametrics V389 operated at these frequencies of 500 kilohertz, and we have an acquisition system, a signal generator, and the diagrams, the pictures over here show the setup in the water. So you see the V389 transducer over here. This is a concrete block over here provided by Dr. Creswell. You can see the rebar over here. This concrete block was very recently put together, and so corrosion was really not expected to be significant at that point. So this was the very first sample that was actually given to us, and this is the focus of this talk today. But we have additional concrete blocks showing much more advanced signs of corrosion, which are being analyzed now. So you can see to the right the experimental setup, and the transducer moves pretty much from along the rebar showed over here. Now, when we actually perform the measurement, we place the transducer at different positions. And what you can see here is the transducer signal followed with, the transmitted signal over here, followed over a certain period of time with the echo from the concrete. And then afterward, the first echo from the rebar. And this is as a function of time in microsecond. And here along this axis is the record for various positions of the transducer. Now, these echoes that you see here are obtained after performing an average across 10 records. So we actually place the transducer 10 times in the same position, perform the record, time align everything, and perform an average across these 10 records. And the objective is to reduce the background noise. Now, this over here very quickly shows an overlay of the echo produced by the concrete block. Once again, these are measurements versus the echo produced by the rebar. You can see the difference in amplitude of the echoes. Clearly, obtaining an echo from the rebar can be tricky. Now, the next thing we do is, I'm keeping track of time over here, is perform the modeling. So here's the biomodel. And now I do not have time today to present the biomodel in any detail, but on Thursday, I'm actually going over a seminar for an hour. I'm going to give a seminar for an hour, and I will provide at that time the detail of the biomodel itself. But you can see the parameters over here, and probably the most important is the fact that thanks to Dr. Creswell, we knew the concrete composition. So we had 16.6% cementite, 33.4% sand, 43.1% coarse, 6.8% water. We were in a saturated situation. And so we actually used these parameters along with porosity information in the concrete to actually create this set of coefficients, which are actually very, very useful coefficients when we actually intend of studying the characteristics of the concrete block. And so you can see over here, we have the bulk modulus, mass density, fluid viscosity, and so on. And this is, keeping a track on time, I think I'm almost out of time here. This is in blue what the measurement was, and in red what the model produced. And they are exactly time aligned. So there's a really good time alignment, there is a really good amplitude, and there is a good match in amplitude, and there is a good match in shape. However, and this is going to be the conclusion of my talk, if you look at this last figure, you will notice that there is a little bit of a discrepancy in the second half of the echo from the rebar. So this is the echo from the rebar in blue measured, in red simulated, and in blue, over here is the echo from the concrete surface. So we actually are working on improving the quality of the second echo, that coming from the rebar. And this has to do with the fact that the sound actually travels as the impulse hits the rebar. It travels through the rebar and bounces, and it causes the rebar to vibrate and oscillate on its own. And we're actually improving the biomodel to perform a better match, accounting for the thickness of the rebar itself in our model. This is where we are right now. So as a conclusion, and I know we are a little bit out of time here, I'd like to mention that we are in the process now of improving this biomodel to actually get a little bit better match with the measurement, performing additional measurements, and with my students, we're actually working actively on optimizing the parameter so that we can finally start seeing if this model is effective at detecting early signs of corrosion. And this is the end of my talk. I would like to acknowledge Tri-Durelli for its support, and Florida Atlantic University, as well as my colleague Francisco Creswell and the Center for Corrosion at FAU. Thank you.